It is section 8.3, Trigonometric integrals, which involve algebraic combinations of the 6 basic trig functions. Let's begin with integrals of powers of sine x and cosine x given in this form. There are 3 cases. Let's see case 1, m is odd. The power of sine is odd. Then m can be written as here 2k plus 1 with k on integer. Then now sine to the m is the same as sine to the 2k plus 1. So it can be written here sine squared and kth power times sine. Just a moment, disappeared. Sine. So here, the sine squared is the same as 1 minus cosine squared. And we have this term and sine x. Now, sine to the m is changed in this way so that along with the cosine to the n, now that portion will make a function of a cosine x. And once we use a substitution u equal cosine x, then du must be minus sine x and dx. This sine x will be used to along with delta x to make du. Here, the key idea is that we try to change, and sine and cosine are combined, then we try to make a function of one of them, and then we try to put aside the other one, so that in this case everything is changed into a cosine part, so that it becomes a function of cosine. Now we put aside sine x to make du. That's the idea. So here, now n is 2k plus 1, then we can put aside the sine, and now the remaining part will be odd power, even power, and then along with that here, we can change this portion as a function of sine, so that everything becomes a function of sine, and we have now cosine and extra, so that if we are using substitution, u is sine x, then du can be easily now here written along with the cosine x and dx. So that's the idea. We put one aside, and then for remaining one, we try to transform so that it is a function of cosine or sine. Okay. Now, m and r, both m and r even, then we may try to use half-finger formula so that here the power down, then and after that, and one of them becomes odd, then we can use one of these techniques. If not, then we can go further. Okay, here, let's try to solve these problems. Evaluate the integrals. Okay, for here, this power, that power, simultaneously odd, so we can use one of them. Okay, let's begin with this one. That is same as now cosine squared, so it is same as 1 minus sine squared x, right? And then cosine x. So here, if we are using substitution, u is now sine x, then here du will become cosine x and dx. So here the given integral is same as integral sine to the 5, so the u to the 5 and here this portion is 1 minus u squared, and cosine x dx will become du, right? Okay, the first term is power 5, so that its antiderivative is 1 over 6 u to the 6, and the second one is a 7th power, so that 1 over 8 and u to the 8. Now integration constant. Okay, u is a sine x, so that the final answer must be 1 over 6 sine to the 6x, and minus 1 over 8. Now here sine 8th power of x plus c. That's the final answer. Okay, for this one, already here we have only one term and 5th power, so that we can put one sign aside. And now for sine to the 4th power, and we try to change the term and as a function of a cosine. You can do it directly. However, let's try a little bit the change of variable practice. Okay, first we try to change 3x and to become t. T is now 3x. Then here dt will be the same as 3 dx. So this portion, that portion will make a dt. Okay. Now x is 0 implies t is 0. Now x is pi over 6 implies t is pi over 2. Okay, using this data, the given integral becomes here from 0 to pi over 2 integral, and sine to the 5 is just simply sine to the 5, and 3x becomes t. Now 3 dx becomes dt. Okay. Now here for this portion, okay, for this portion we can separate this one. Okay, sine. Okay, let's try to use just s rather than sine, so that is s to the 4 times s. Okay, s squared is same as 1 minus cosine squared, so that is 1 minus c squared ns. Right? Now, if we are using substitution, okay, u equal here the cosine t, then here du must be minus sine t and dt, so that this portion and that portion will make minus du. And here now t is 0, then u is 1. Now t is pi over 2, then u becomes 0. So here the given integral will change it into 1 and 0. It's a lower bound and upper bound. Now for this portion, it's the same as 1 minus c squared, and so that 1 minus u squared squared. So let's try to put in this way, 1 minus t2 u squared plus u to the 4, right? And then now sine t dt will make minus du. Okay, so you may rewrite this one in this way, along with this negation, and change the lower and upper bound will be cancelled out, so that from 0 to 1, now 1 minus 2 u squared plus u to the 4 du. Okay, now from now on, the integration is a piece of cake. You can finish yourself. Okay. Okay, now we'll try to solve this one. Now cosine squared. So it's quite easy. By using half-finger formula, we can write down that on as now half of 1 plus now cosine 2x and dx. Okay, from now on, they are sum of elementary derivatives, so that you can finish it quite easily. Okay, that is half will come out, that is x, and that is now half of sine and 2x and plus c, right? Okay, now we'll go this problem. Sine squared cosine fourth power. For that one, okay, let's write in this way. Sine squared will be half of now 1 minus cosine 2x, right? And then for this one, cosine squared and squared, so that cosine squared is half and 1 plus cosine 2x squared and dx, right? Okay, so the coefficients, the constant will be 1 over 8, and integral we multiply out, then that is same as 1 minus cosine squared 2x. Okay, we'll write here 1 minus cosine squared 2x, and here one more 1 plus cosine 2x dx. Okay, for this one, okay, let's read it again. Here, integral, that is same as 1, and plus now cosine 2x, that is now minus here cosine squared 2x, and that is now minus cosine third power 2x now dx, right? Okay, for this one, that one, you can find the antiderivative quite easily. Now for that one, again, you can use the half-angle formula. Okay, for this one, you can use a half-angle formula, which is now half and 1 plus here cosine now 4x, right? Okay, so again, and that on everything are easy to get, and their antiderivatives. And now for that one, okay, we'll focus on that term, integral of cosine third power of 2x. Okay, that one. Then again, we put aside one cosine and 1 minus, okay, now cosine squared will change it into 1 minus sine squared. So that is same as here 1 minus sine and squared 2x, right? And then here cosine 2x dx, right? Okay, if we are using the substitution u is sine and 2x, then now du will become 2 of cosine 2x and dx. So this portion will be changed into half du. So that one is the same as here integral, and that is 1 minus u squared, and that is half du, right? So that is half of now u minus 1/3 of u cubed and plus c. So that is same as 1/2, and u is sine 2x, so that's sine and 2x minus 1/3 of now sine third power and 2x, okay, and plus c, right? Okay, and so integral of this term is now known. So for others, you can find it quite easily. Okay, try to finish yourself. Okay, for that one, now 1 plus cosine 4x is not elementary derivative, but here, if we start with cosine squared 2x, then by using the formula, we can get 1/2 of 1 plus cosine now 4x. So here, square root will, so that basically this term inside radical is same as twice of cosine squared 2x. So that radical is the same as now, square root of here 2 cosine squared 2x, right? X will move from 0 to pi over 4, so that now here we can eliminate the radical along with 2 without absolute sign. Now number will be square root 2, and then now this cosine 2x. Now that is positive between 0 and pi over 4. So here the given integral is the same as, now square root 2 can go out, and from 0 to pi over 4, and cosine 2x and dx. Okay, so that is square root 2, and that is same as half of sine, now 2x, evaluating from 0 to pi over 4. So pi over 2 will be 1, so that is same as square root 2 over 2. That's the final answer. Okay. Okay, here, now secondly, we'll try to evaluate integrals of powers of tangent x and sec x given in this form. Now, also we have 3 cases. Don't try to memorize these cases. Just basic idea. The key idea is that we'll substitute u equal tangent x or u is sec x. And now once you try to use this substitution, then you have to put aside sec squared, because derivative of tangent x is a sec squared. So you have to make some portion, you have to consider for du. Du must be well defined, easily defined. And now derivative of tangent is a sec squared, so we put aside the sec squared, and then here we can use such a substitution. If you want to make substitution u is sec x, then du must be sec x tangent x. So when you try to change the format, then you have to put aside that portion, so that everything else must be function of x. Of course, in this case, you put this term aside, and everything will be now a function of a tangent. How? By using this formula. Earlier, we tried to use sine squared plus cosine squared is 1. Now we are trying to use sec squared is 1 plus tangent x. Its variant is given in this form. Don't be confused here. Sec is 1 over cosine. The sec is always larger than 1 or smaller than minus 1. So that this is always, squared is always larger than 1, larger than or equal to 1. But a tangent squared x is now larger than 0. By adding 1, and they can match each other, right? So that, and also here, tangent start from 0, but sec squared start from 1. So with negation 1, they can be the same. Okay, so that don't be confused for the formula. Okay, now otherwise here by using now these identities, and then now also some integration by parts. Maybe you may have to use integration by parts first and then use these formulas. Okay, now let's try to solve some problems. Now for these problems here, for instance, now sec to the 4, if we try to put sec squared aside, then now remainder part is sec squared. Okay, that one. Now that is the same as, oops, here the pen is not well working sometimes. Okay, now sec to the 4, that is same as sec squared x and sec squared x. Now this term is the same as 1 plus tangent squared, right? So that is now here 1 plus tangent squared x and here sec squared x. Now we can use the substitution u equal tangent of x. Then from here du will be sec squared x and dx. So this portion and that portion can be replaced by easily here du. Okay. Okay. So the given integral can be written in this way. Now the first one is now u squared, and then this portion is same as 1 plus u squared, and sec squared dx can be now du. It's simple, right? Okay, that one is now 1/3 of u cubed, and plus there's a 4th power, so at 1/5 of u to the 5 plus c. Now u must be replaced by tangent x, so that now 1/3 tangent 3rd power of x, and plus here 1/5 and tangent and 5th power of x plus c. That's the final answer. Okay, for this one now okay, if you try to put aside, for example, sec squared, then 1 sec remained. So by using that, you cannot change that as a function of tangent. Of course, you can do that, but the radical will appear. So that here, rather than that, here we try to put aside tangent and sec. That one is the same as now tangent 4th power of x, and then now sec squared x times here tangent of x and sec of x, right? Then we may try to use the substitution u. Okay. Now u is here sec x, right? U is sec x. Then here du equal, now that is now sec x and tangent x and dx, so that this portion and dx will make du. Okay, for this one, tangent x is now same as, okay, sec squared minus 1 is square, so that given integral is the same as here integral. Now that is sec squared minus 1. So that u squared minus 1 now squared. And then sec squared is now again u squared. And here remainder part is du. From now on, the computation is not so complicated. You can finish it. Now this is polynomial of u, and you can get antiderivative quite easily, and u must be replaced with sec x. Then that's it, right? Okay, let's try to evaluate this integral. Sec cubed x, and now for that one, we cannot put aside sine sec squared, and we cannot put aside sec and tangent. There's no tangent here. So in this case, here I mentioned in here, you may try to use the formulas and use integration by parts. So here the hint is given. U is now sec x and v is sec squared. Then from here v is antiderivative is the same as tangent x, right? So the given integral is changed into uv, that is sec x tangent x, and minus u prime, that is here sec and tangent, and v is tangent. So that here now sec x and here tangent and one more, so that now we have that, right? Okay, for this one, now here, okay, we may try to use the formula. For example, now for that one, tangent squared, that is same as sec squared x minus 1. So that this portion can be written here. Now that can be integral sec, oops, I forgot s here. Okay, sec cubed x, and then now minus integral sec x, right? Okay, so here now sec cubed x is what we have to get. So here we have one more, and along with negation we have that, so that basically once we move this into right side, left hand side, then that will be twice of g given integral. That is same as this term minus, so that along with this negation plus sec x, so that g must be half of now sec x and tangent of x, and plus integral now sec x, right? Okay, now sec x for that one, and already you learned that we try to multiply sec x plus tangent x over sec x tangent x, and so that the same term is multiplied the bottom and top, then you'll see that top becomes now the derivative of this term, so that eventually the integral of sec is same as logarithm of sec x plus tangent x. So you can use this one over there, and now integration constant is given, then that's it. So here we'll finish it. Now that is here now 1/2 of that term, and plus logarithm of now sec x plus tangent x, and here plus c, integration constant. That's the final answer. Okay, now here we have this term between that computation, so that now from this one, if you try to do, then you reach at this one, and if you are using the formula, then now you have to get that one again, so that eventually it appeared during the computation, so that this term, now that is unknown, we want to get, that is the same as here, now this term minus g over there, right? We already got this one, so that from part A, we can see that is the same as, now, okay, this term minus g, so that is a sec x tangent to x, and minus g minus half of, now, okay, sec x and tangent to x, and plus and logarithm here sec x and plus tangent of x and absolute sign close over there. Okay, now it's h, so that it's not easy to make. Okay, now that is C. Okay, that's the final answer for that one. Okay. Okay, sometimes we have to use such a formula. Now, sine 3x, cosine 5x, they are different. Then we can use such formula. That is half of sine a minus b and plus and sine a plus b for sine a cosine b. So over there, the integrand must be now sine a cosine b. So that is same as half of now sine a minus b. So then sine minus 2x. So that we can say minus sine 2x and plus, and if we add them, then sine 8x, right? So here is antiderivative can be easily gotten here now. Half can go out, and antiderivative of that one will be now half of cosine 2x, and that antiderivative will be minus 1 over 8 and cosine here 8x, right? Plus c, and integration constant. Okay. That's the end of the section 8.3. Thank you.